going to take a look at Chapter 5, Section 7, Constraints and Statistical Determinacy. Okay. There are certain cases where you have a problem, and it could be that you have more reactions than you have uh, equations, independent equations. And an example of this is here. Here's a problem here where you have where you look at this problem, you have fixed support and you have reactions about each of the axes, and you have reactions in each of the directions, and you also have a bearing over here, support, and this one has two reactions associated with it. Okay, so um, with a problem like this, I now have eight unknowns, and with my equations, I can only come up with six. I can only solve for six of them. Okay, so this is called statistically indeterminate, all right, or a redundant constraint. So it could be, in certain types of applications, it's designed where there's some redundancy built in, so that the you can protect a system from failure by doing that. Okay, so there is some redundancy built in a lot of times just for failure protection. We also have problems where there's improper constraints. Okay, and in this case, um, you have equations of equilibrium, but it's not properly constrained, right? So it may become unstable in certain conditions. And here's an example here where you have like a pin support and you have a roller over here. So you have reactions. This provides reactions in the x direction, one in the y direction, but there's no reactive moment here. So, and this force is acting at a distance from this support. What's going to happen, as expected, is this is going to rotate about A. Okay, so this is a situation where it's improperly constrained, right? Typically undesirable in our statics problems, right? Okay, so here's example one. Let's take a look at this problem. We can look at the different reactions that are provided for the different forces. Okay, so in this problem, you have a force pushing down at this location. You have one end of the rod is connected to this cable, and you have a bearing over a thrust bearing or journal bearing on the left here. Okay, so this thing can slide in and out if needed. All right. Um, this cable, if you think about what kind of reactions it'll provide, it's like, yeah, this thing can swing back and forth in any direction. It can't really go down. It could go up, but if you're looking at this force in the directions it's acting, if we draw this as a reaction going up, or pushing up on this direction, and the number comes out to be positive, then of course we know that we had it in the right direction. Okay. So the first part of this is in a problem like this, you come up with your basic approach. But our basic approach for here is we come up with our free body diagram, right, of this system with the reactions in place. Okay. Oh, let me go back. Oh, go forward again here. Okay. So however you establish these axes, well, ours already had the axes defined here. So in the original diagram. Then we draw the free body diagram of it. Of course, we're going to write the scalar equations for those, right? We have the moment equations, and we have, you could write it, the forces, you could write them as scalars, or you could write it as a vector if you wanted to. But we're going to look at it with just scalar equations. And then you're going to apply these in equilibrium to solve for the unknown forces, okay? This is the author's approach. But any situation like this, you could have, put this as a three-dimensional system and then solved it that way. Okay. All right. So first part, X, Y, and Z, we already have those. And now what we're going to do is put in the reactions. Okay. So we have a reactive force in this direction, and of course, this bar can slide in and out. So there's no reaction. along this axis, which is our y-axis, okay? So a problem like this, it might be that, you need to set up these axes, and you would set it up something that works out pretty conveniently, like this problem was set where this bar was right along the y-axis. So you can see that sliding in and out would mean that, of course, you have no reaction in that direction, okay? For convenience, you have that. All right. Now, now it can rotate about this axis, so it does not provide any reaction there, right? And now the cable. The cable only has a z component up and down, all right? Okay. And then we have the force here. So now here are all of the forces and reactions, which are reactions are forces too. These are all the forces that are involved in this problem. All the reactions, reactive moments, and forces that are involved in this problem. Okay, so our free body diagram is correct. Okay, so first part, you can sum all the forces. So summing all the forces in the different directions to solve for those unknowns. Okay, so we need to find this AX and AZ. All right, so the first part is you'll notice that when you come up with the summation of the forces in the X direction, this is the only force we have, right? There's nothing else here. So it's simply just a matter of saying AX is equal to 0. So there is your reaction in the AX direction. There's no reaction really, okay? The next one we could do is the AZ direction. So we have we have a force vertically right here in the Z direction, which is a reaction, and we have a force acting down, and then we have one over here. So the equation just becomes AZ up, FBC is up, which is positive, and the 80 pounds going down, which is negative, right? Well, we have two unknowns, so we cannot complete the solution at this point just yet, all right? The next thing we could do is think about having a moment about an axis. And like I said, it's really, you could do this three-dimensionally if you wanted to and create everything as vectors and then just figure it out from that point. That's another approach. The author chose to use the approach of making this like multiple two-dimensional problems, essentially. Okay. So if you think about it, let's look at it about the y-axis first and see what kind of moments there are. So right along the y-axis, you'll see that these points, these forces intersect along this line. So because they intersect along this line, these two forces here, they have no impact on the moment about this line, okay? Now, what we're going to have is we're going to have a force acting down. And if we're looking at it from like the positive y-axis, what we notice is that this force going down is going to cause clockwise rotation about this, okay? So it's going to be 1.5 times 80, which is negative, all right, because it's causing clockwise rotation. So you're basically looking at it like from, the plane that you're looking at is the XZ plane, and you're kind of looking at it from perspective over here, looking straight down into it, okay? So that now gives us our new equation for that. And you'll notice that in this moment equation, the only thing we don't know is FBC. So you can very easily solve for that. Then you can take this, plug it back into this equation, and then solve for AZ. So right now, we have reaction here, here, and here. We've solved those reactions. Okay? All right. Now what we need to do is we need to solve for MAX and MAZ, the reactions along those axes. Okay. Now, you have some choices here. Of course, you could write it about an axis if you wanted to, or you could write it about a point, right? You also have points in these. So in this case, okay. Okay, so for this one, we'll start with looking at it from the x-axis. So we now have a plane of z and y, and we're looking at it straight through here, okay? Well, first part is that along the x-axis, we're going to have this reaction. All right, so that's defined. That's our reaction about that axis, and it really is any point along this axis, right? So here's our reaction do this. This is in a totally different plane, so we don't have to worry about this one. And what we have is here's our MAX, and we've drawn it a counterclockwise rotation, so it's positive. And then what are we going to have? We're looking at it. We're going to have this force acting at a certain distance, and we're also going to have this force acting at a distance, right? So you're looking at it from like the front side, and like I said, you have a plane now made of Z and X, and both of these, as far as this axis is concerned, both the 80 pounds and the 40 pounds FBC are both acting at 6 meters, or sorry, 6 feet from this axis, okay? And if you're looking at it from the front perspective, the 80-pound force is going to cause clockwise rotations. That's why it's negative. And the 40-pound is going to cause a counterclockwise rotation about this axis. And that's why this one is positive, okay? So you can go right in here. You can solve for that. So you can solve for this reaction, MAX rate, from this equation, okay? The next one is MZ. Now, the same thing here. You're looking at it like from the perspective of Z, so you're looking straight down this axis and you're looking at it on this plane, okay? Now, what you'll see is that now you have forces. These two are parallel with Z, so they have no impact on that rotation about the Z axis, okay? So with that in mind, since they have no, these are the only two forces involved, this is on a totally different axis from us, is that, or the reaction's on a totally different axis from this, so it actually goes right through this. It's 90 degrees off from this, so it has no impact on it. So we just have the reaction at MAZ here, and that, of course, is equal to 0 because there's no forces along that plane, right? So the last one is MAZ equals 0. So these are all the final answers. Here's the reaction at point A, and the reactive show that couple moment along the x-axis. Here it is along at point A along the z-axis. And here's the force, the reactive force of this cable. AZ is the reaction at at point A along the z-axis, and here's the reaction at AX at point A along the x-axis. Okay, here's another problem. All right, and the approach is going to be the same as what we previously did. Okay, you have your x, y, and z, and you can typically in this class we draw the z vertically and the y off to the right and left. Following the right-hand rule is fine as long as you follow the right-hand rule. And we've drawn them like right along these lines of this plate, rectangular plate, right? So same thing as before. We come up with an axis, establish these axes, come up with draw the free body diagram, write the forces using the scalar equations, and we're going to do it two-dimensionally. Okay. So if you think about looking at the forces that are involved, what are you going to see? You're going to see force acting down. You're going to see a tension here, tension up, tension here. Okay. And then the moments, we'll take a look at those moment equations and how we're going to actually go about and come up with the ones to solve it. All right. So right off the bat, we look at it. We're trying to find the tensions. We have 3 unknowns, right? So we know we're going to need 3 independent equations to solve for those. Okay. So from the free body diagram of the plate, and the other part, of course, is the, sorry, I forgot one part here. The plate weighs 500 pounds, so we need to put that at the center of mass of this plate, the center point or center of area. It comes out to be the same, okay? So we draw that in. So we have the force acting down due to the weight and another force acting down, and then we have those 3 tensions, okay? All right. So doing the summation of the forces in the z direction, of course, we come up with an equation. Here's our minus 200. Here's our minus 500. Here's our 3 tensions acting vertically up, and they're equal to, of course, these forces. So we just don't know how it's distributed amongst those yet, okay? The next thing is we can come up with a moment about each of the axes. So the author chose to do it about the x-axis first. So thinking about the x-axis, this TB is acting right on the x-axis, so that's not going to be involved in the moment equation. But we have this force, this force, this force, which is the reaction, and then this is a reaction, and this is a reaction. So we're going to have 4 components for the moment about the x-axis. So we just go over by 1.5 times 500. And if you notice, looking from this direction, this is going to cause clockwise reaction about a clockwise rotation about the x-axis. Okay, so that's this 500. That's what this is, and it's negative because it's clockwise. The 200, also, this is acting at 3 feet, and this one is also clockwise. And then we'll notice about the tensions. Well, these are forces. This one's acting at 3 feet, and this one's also at 3 feet. TA and TC are both acting at 3 feet away from that axis. Okay, and here's the 3 times TA and 3 times TC. Okay, so now what we have another equation, and this equation has 2 unknowns in it. All right, the next thing we could do is do it about the y-axis. In this case, now you'll see the TA goes right through the y-axis, so that doesn't have any reactive moment about the y-axis or any or moment coupled about the y-axis. Okay. Then we're going to have the 200, the 500, TC, and TB as before, except now what we notice the 200 and 500 are at 2 feet. Okay. And you're going to see that those two are counterclockwise now. So those two are the positive ones about the y-axis. Okay. So they would call us counterclockwise rotation about the y-axis. Then the TC and the TB, both acting at 4 feet, would cause clockwise rotation about the y-axis. Okay, so here's the equation with TB and TC. Okay. Okay, so writing down those 3 equations, the way the approach the author took, was just saying, using these 2 equations, rewriting those, putting them in terms of TC. So now you have TA in terms of TC, and you have TB in terms of TC. So now you could use those 2 in this first equation. And now the only unknown in this first equation would be TC. So you could solve for TC. Okay. So with that, mind making these substitutions into that first equation, we now have TC equal to 100 pounds. Okay. So you could take that TC equal to 100 pounds, substitute in here, and substitute in here, and solve for TA and TB. Okay. Okay, so for the next problem that we'll look at, we have another one, a bent rod supported by smooth journal bearings, A, B, C. Assume the rod is properly aligned. Okay, so in that case, if it's properly aligned, then we're going to, there will be no reactive moments at any of these bearings. Okay, so if you think about the reactions at each one, you'd see that, along this, at this one, the y-axis, the rod goes right through, so there's no reaction in the y direction for this one, just in the x and z. And this one there's no reaction in the z direction, and there's no reaction in the x direction. So overall, what we're going to have is there's going to be 6 unknowns. Okay, and follow the usual process. We're going to do the free body diagram, and then we're going to look at applying scalar equations to find these unknowns. Okay, so free body diagram. Here are the reactions. There's 6 reactions, and there's 1 force being applied here. Okay. Okay. So in this case, what you can do is you can start off by breaking up the force into its components, its x, y, and z components. And this is just the same as what we had previously done. We have like, if you wanted to think about this as some vector f prime right here, and you have this 60 degrees. So to figure out the this component, which is your z component of the force, it's just going to be that 60-degree angle here relative to the xy plane, and it's just going to be the sine times that. That's what this is right here. Okay, times f was given as 800 newtons. Okay, So then after that, you use that um, the this vector right here, which is the cosine times of 60 degrees times this force vector 800 gives you this. That is the component, this vector right here. Now you take that vector, the one that you makes this line essentially, which is along the xy plane. You take that vector and you break it up into its two components, right? So this is that vector. This vector right here from here to here is the 800 cosine of 60. So that's the magnitude of that vector. And then you just use the cos multiplied times the cosine of 30, which gives you the x component. And then the sine of 30, which is this line right here. Okay. So now you have the forces. And you can separate that out into three-dimensionally, right? Your I, J, and K components for the force. Okay. Okay. So then what you can do is apply the scalar equations for that. Okay. So you're going to have in the x direction, AX, CX, and then the 346 was right here. That's the I component of the x component of the force. Then we do the same thing in the y direction. So we have the 200 and the by and the cy. And in the z direction, we have the 692, and we have it as az and bz. Just one thing to note here, this should be a negative, okay, because it's going down. Here the positive z is going up, so there's a little bit of an error here. This should be a negative 692.8, okay, and that's what you'll see in here. So it's a minus 692.8 here, okay, so this should be a negative. All right, so now what we can do is we can actually do we have equation with, of course, some unknowns. And what we can do is use the summation of the moments about the x-axis, starting with that first, and then do it about the y, and then about the z. Okay, so we're doing it about the x-axis. So x-axis is right here. So there's no components. These two are right along the pass through the x-axis, so they don't contribute at all to the moment about the x-axis. And also cx, that's parallel to the x-axis, so that doesn't contribute anything either. So what you're left with is the cy times the distance, which would be the vertical distance here. So that's times 2. And if you think about what it would cause, this would cause clockwise rotation about the x-axis. So what we're doing is we're taking, essentially you're looking at it directly along the x-axis, positive x-axis, and you're seeing it in the plane. Okay. Then BZ contributes about it. Now this one you can see it's pushing straight up. So about the x-axis, this will contribute it'll be positive. So it's going to be 2 meters times the BZ. Okay, and that's what this is. Then the last one here, the minus 692.8, is going to be, it causes clockwise rotation about this axis. Okay, and because it's going straight down here, and it's off 2 meters. So that's where you get this 3 components here. Okay. All right. The next one is my, and here's the y-axis. So right along this line, you think about the bz contributes something to cause rotation about this axis. By doesn't. Cy doesn't because they're parallel to the y-axis. So we have a bz, and we have cx. And you can notice these these also pass right through the y-axis, so neither one of these contribute anything to the moment about the y. And both of these you'll see bz and cx. So cx cause counterclockwise rotation like this. So if you're looking in straight in from the y-axis, and the z and the x plane cause counterclockwise rotation about the y-axis. That's what this is. And then, oh, sorry, this one. And then by, and sorry, not by, it doesn't cause anything. Bz, that's going to cause, if you're looking at it from here, also counterclockwise rotation. So this causes counterclockwise rotation, and this one causes counterclockwise rotation. Okay, so both of them are counterclockwise. Okay. All right. Now m of z. Now this one, we're kind of looking straight down at it, and we're looking at the XY plane. Okay. So first part is we're going to have, so it's CY times 1.75. Okay. So we're looking straight down, and we're looking for the distance. Uh, so looking at the distance, you think about like the distance from here over. You draw the line CY straight across, and you'll see that where it actually meets the closest place on, at 90 degrees, meets this axis at 90 degrees, would be straight out here, which means it's the 1.75 meters, this distance from here to here. That's the first one. And that would cause clockwise rotation about Z. Right? The next one is the CX. Now CX, if you drew a line straight out here, it's going to meet at a distance of, from this point to here, essentially straight up, and it's going to meet at a distance of 2 meters. And that one also causes clockwise rotation about Z. The next one is BY. Okay, so BY, if you draw this one straight back here, it's going to be 1 meter. So 1 meter from here to meet that, intersects with that line of action of that force BY. Okay, and it's going to be negative because it causes clockwise rotation about Z. Right. Then the last one is the 346. Now this is the X component of this force. Okay, so that's the component that's like going straight along here, straight along this line. And if you look at it, it's going to also cause clockwise rotation about the Z-axis. And it's times 2 because it's 2 meters away from it. And that's the last one for that. Okay. So now we have 6 equations with my 6 unknowns. Okay. Now, what you could do is use Cramer's rule to actually go through and solve these. So it takes a bit of work to set these up and solve it. Let's see. You should be able to set up these equations, like summation of the forces in all of the directions, x, y, and z, and the summation of moments about these axes, right? And this is similar to what we had previously done on previous problems. The only thing, this was a negative over here, okay? So you could go through that process, and I actually was looking at some tools online even, and here's one. This is matrixraj.com, kramer.php. You can actually, you could set up your equations and you could have 6 variables here. You could set them up and then substitute in and have it solve it for you if you want. If you want to do that, you can go ahead. But otherwise, I won't. My expectation is it's just too time consuming to do this. Okay. But you could set this up. It's not that difficult to go and set up these 3 equations. Okay. So that's that. Okay. And just we looked at different supports and just the static equilibrium cause sum of the forces and sum of the moments about any point to be equal to 0. Okay. And that pretty much ends this section and this chapter from what we were going to cover in this chapter. But I'll spend some time going through some of the problems.